Good morning, everyone. Welcome to my PhD thesis defense. My thesis titled as Fairness-Aware Optimal Resource Allocation for Non-orthogonal Multiplexers or NOMA. Before moving into the technical contributions, let's first look into the outline of my presentation. First, I will discuss NOMA as a key next-generation multiplexers technique and its challenges in resource allocation. And then I will briefly discuss a few problems that I have explored during my PhD. The first one is NOMA in frequency-selective channels. And the second one is multi-user NOMA and some rate fairness trade-off. And the third one is semi-grant-free NOMA. Finally, I will conclude with key contributions and discuss a few future research directions. Before moving into NOMA, let's first look how multiplexers techniques have been evolved across different generations. As wireless systems evolved from 1G to 5G, we have seen different multiplexers techniques like frequency division multiplexers, time division multiplexers, code division multiplexers, and orthogonal frequency division multiplexers. These multiplexers techniques are quite different in nature, but they all share one common principle. Here, all the users are separated using orthogonal resources. This orthogonality simplifies the receiver structure design and eliminate complete multi-user interference. But at the same time, it has limitations. The first one is that it restricts the number of users that can be simultaneously served. Why? Because the number of users that can be simultaneously served is directly tied up to the number of orthogonal resources, which limits cellular system capacity and scalability. And it is also inefficient in accommodating users with diverse quality of service requirements. For example, when a user, sorry?
Keep going.
Okay. For example, if a user is requiring a very less low data rate requirement, but still if it's using a complete orthogonal resources, it's just underutilizing the spectrum resources. So here, the natural question arises is here that instead of avoiding or eliminating the complete interference, can we manage interference intelligently and allow multiple users to share common resources? That is precisely the idea behind non-orthogonal multiplexers or NOMA. In NOMA, multiple users share the same time frequency resources. There are different types of NOMA. One of the most widely used is power domain NOMA, in which users are separated in power domain. At the receiver, we use successive interference cancellation or SIC to retrieve data. For example, let's look into a two-user downlink NOMA system in which the base station sends the superimposed signal of these two users, whereas at the receiver, at each user, successive interference cancellation is used, and it first decodes the other user's signal and then cancelling out from the total signal and then decodes its own data without any other interference. In general, NOMA increases throughput, reduces delay, and improves connectivity, which are key requirements for the next generation wireless systems. However, the performance of NOMA critically depends on how resources such as power, transmission rates, and decoding orders are allocated among these users. So we have to, and that is exactly the question we have addressed in this thesis. How do we design practical resource allocation algorithms that can realize the performance gain of NOMA? So first look into the practical challenges in these resource allocation problems. First, it has to be compatible with the 5G 6G physical layer. What does that mean? We cannot assign any arbitrary transmission rate to these users. It has to be constrained by a finite discrete set of modulation and coding schemes that has been specified by the 3GPP standard. Here in this table, we are just listing a few modulation and coding scheme indices, their corresponding modulation schemes like QPSK 16 QAM and 64 QAM, and their rates in bits per symbol. Here in this figure, we can see that in discrete rate models, a range of SNR corresponds to a particular rate. which is different from the continuous rate adaptation models that have been widely used in the literature. NOMA must also operate over orthogonal frequency division multiplexing or OFDM. In OFDM, the system bandwidth is divided into physical resource blocks as shown in this figure, and each resource block consists of 12 subcarriers. Another practical consideration is the common modulation and coding scheme power constraint. What is it? In frequency selective channels, the channel gain across the subcarriers for a given user is varying, as we see in this figure. But at the same time, the standard mandates that the same modulation and coding scheme and power must be used across all these subcarriers, even though they see different channel gains. It reduces uplink feedback and downlink control signaling overhead. Another practical challenge is the fairness among the users. As we know, different users experience different channel conditions. Always maximizing sum rate or throughput will not be optimal. Why? Because it will get disadvantage for the weaker users which are sitting at the cell edge, for example. Another practical challenge is the imperfection at successive interference cancellation. In practice, decoding can never be perfect. There can be errors, and these errors will propagate through the stages of successive interference cancellation. Therefore, to design a good or efficient resource allocation algorithm for NOMA, we have to consider all these factors jointly. Next, let's look more into NOMA, the decoding orders and the resulting HCNS before we go to the key contributions, the main problems. So let's look into the new two-user NOMA downlink system, where there is one near user and one is far user. And we are using the discrete modulation and coding scheme table that have been specified by the standard. And here P1, M1 are the power and modulation and coding scheme given for the near user. Similarly, P2, M2 for the far user. At the near user, at SIC, it first decodes far user's data. And its SINR is given by the signal power divided by interference from the near user plus noise power. And then it cancels out the far user's signal and then decode its own signal without any other interference. And thus there is no more interference. So it's just SNR. Whereas at the far user, it decodes its own data with the presence of interference from the near user. That's why this interference term is coming up. This decoding order, we call it as farthest to nearest decoding order, which is widely used in the NOMA literature. Here we note that the far user's data have been decoded twice, one at the near user and one at the far user. Having understood this, now we are ready to move to the problems that we have addressed in this thesis. So the first problem is NOMA in frequency selective channels. Here we are considering power domain NOMA in a frequency selective channel. Here there are two users, one is near user and one is far user, and we are considering frequency selective channels. And we can see that across the resource block, the channel gain is varying due to frequency selectivity. And we also account for the common modulation and coding scheme power constraint. That's why at each user, we have to use a common modulation and coding scheme, let's say M1 and power P1 at the near user. Similarly, the same M2 and P2 across all the resource blocks for far user. Here, our goal is to maximize weighted sum rate by choosing optimal modulation and coding schemes M1 and M2 and powers P1 and P2 subject to block error rate constraints of these two users. We define block error rate as the probability that a user's packet is decoded incorrectly. Before moving into the problem formulation, let's first look into the SINR or SNR expressions at near and far user. Here, we are using farthest to nearest decoding. So at the near user, it first decodes far user's data. On the nth physical resource block, we can write the SINR as signal power divided by interference from the near user on the nth physical resource block plus noise power, and then decode its own signal without any other interference. So its SNR expression is shown here. Similarly, at far user, it decodes its data in the presence of interference from the near user. So that's why this interference term is coming up. So here we try to formulate the optimization problem as maximizing weighted sum rate. Here, RM1 is the rate of user 1 and RM2 is the rate of user 2, and we are giving a weight to the far user such that we give more priority to that user such in a way like W2 is greater than 1. So we try to maximize weighted sum rate subject to the block error rate constraint of user 1. We say that the block error rate while decoding user 1's data should be below a threshold, epsilon. And since block error, the for users data is decoded twice, we have two block error rate constraints for user. So we say that the maximum block error rate should be less than or equal to epsilon, the threshold, and then there is a total power constraint. Here we want to find M1 and M2, which are coming from a discrete set, and P1 and P2 are the continuous power variables. So since M1 and M2 coming from a discrete set, this problem becomes combinatorial in nature. And we can also see that these are vector of SNRs and SNRs because of the frequency selective channels. This problem is intractable. Why? Because the block error rate of an modulation encoding scheme when transmitted over n resource blocks with different SINRs is not known in the closed form. So how to deal with it? For that, we are using a technique called exponential effective SNR mapping. In this, or EESM. EESM maps a frequency selective channel into flat fading channel. We map a vector of SNRs into an equivalent SNR in an AWGN channel that results in the same block error rate. To verify EESM, we are plotting block error rate as a function of SNR for different modulation encoding schemes. Here, the blue solid curve is shown for the AWG block error rate of an MCS modulation encoding scheme in an AWGN channel. And the scatter plot is shown for EESM. Here we can see that the scatter plot almost follows the blue curve with minimal spread, showing the accuracy of EESM across different modulation encoding schemes. We also note that EESM has been extensively used in 3GPP system level simulations. So using EESM, we simplify our problem statement. So maximize weighted sum rate subject to, we say that the effective SINR of user 1 should be greater than or equal to the threshold of that particular modulation and encoding scheme for the specified block error rate. It's equivalent to the block error rate constraint. Similarly, the block error rate constraint of user 2 also maps to this and the total power constraint. Here, we note that the SINR of user 2 is using EESM equation. We write like this. Here we can see that the effective SINR of user 2 is nonlinear in powers P1 and P2. So how to solve this problem? For that, as I have already told, this is combinatorial in nature. So what we do is that we take one modulation encoding scheme pair for a given M1, M2. We will check whether there exists a feasible power allocation P1 and P2 that satisfies these constraints. So our approach goes like this. So let's say we have M modulation encoding scheme available. So on the x-axis, it's M1, the modulation for the MCS for user 1, and M2 on the y-axis for user 2. And for each modulation encoding scheme pair, we check whether there exists a feasible power allocation or not. If it exists, then we say that that particular modulation encoding scheme is feasible, otherwise not. So here the green ones are the feasible MCS pairs, and among this, we will select the highest weighted sum rate as the optimal one. But how to find the feasibility of a given MCS pair? For that, we are using a numerical approach first, in which we propose a barrier function, which is a combination of two block error rate constraints. And we are using exponential function to come up with that barrier function. Let's see, we can see that the exponential function looks like this. And this is the block error rate constraint of user 1. So when So when the constraint is satisfying, the block error rate is satisfying, the function takes a lower value. But when the constraint is not satisfying, the function itself is blowing up. So we try to minimize f, the barrier function, using gradient design such that we can find the powers. So we say feasible solution exists if even the power satisfies all constraints, block error rate constraint. And we say that an MCS pair is infeasible if no power location exists. But here, for each modulation and coding scheme pair, we have to do this gradient descent. So the natural question here is that can we reduce the complexity? For that, we are using a numerical approach, an analytical approach. For that, let's remember the effective SINR expression for far user, this user 2. We can see that the effective SINR is non-linear in powers P1 and P2. So motivation is that can we take this P1 and P2 outside this equation and make or construct the block error rate constraint linear in powers P1 and P2. Then we can easily solve and find the optimal MCS. And with that in mind, we are proposing a new metric called power-normalized EESM or PNESM. We define PNESM of the kth user with MCSM as follows. Here, this expression is similar to that of EESM, but the only difference is that there is no power term showing up here. Here, alpha is a power scaling constant. GK, LK is the channel power gain between the kth user and the base station on the nth physical resource block, and beta M is MCS dependent parameter. So PNESM definition is independent of power. Now, our next step is to bound the effective SNR expressions, SINR expressions for the block error rate using power normalized EESM and then simplify the problem. So effective SNR of user 1 is upper bounded by PNESM as follows. So this is the effective SNR, we upper bound by the PNESM expression here. And here we can show that this bound is exact for narrowband channel where number of physical resource block is 1. Similarly, the effective SNR of user 2 can be upper bounded using PNESM as follows. For that, we are defining a new metric called SNR K bar, which is the PRB average SNR of the kth user. So for large beta M2 and high SNR 1 bar, we get the bound as follows. Similarly, when SNR 1 bar is small and P2 by alpha greater than or equal to 1, we find or we get the bound for the effective SNR as follows. For all other regimes also, we numerically verified that the bound exists. And here also, we can show that it's exact for narrowband channel case. So using this PNESM bounds, we make the block error rate constraints linear in powers P1 and P2. So the block error rate constraint of user 1 maps to the following, and the block error rate constraint of user 2 maps to this. Here we can see that on the right-hand side, every constraint becomes linear in powers P1 and P2. So now we can easily solve this and find a closed form condition for the feasibility. So here we are showing it pictorially. So on the x-axis, we are plotting the power of user 1, and on y-axis, we are plotting power of user 2. This is the block error rate constraint of user 1, and this is for user 2, and this is the total power constraint. Here, we say that a feasibility solution is possible when there is, say, feasible region AC exists. This is the closed form condition for that. So we found the closed form condition for the feasibility check of an MCS pair. So good enough, we found the answer, right? But there is a catch. Why? Because this linearization using power normalized EESM is a relaxation. What does that mean? The solution, let's say the solution obtained using EESM constraint lies here in this blue. But whereas when we use power normalized EESM, then the solution lies in the bigger circle. So it can lead to an infeasible modulation and coding scheme pair, and thus it overestimates the actual rate. So we need to find some method to or to get the optimal modulation encoding scheme pair. For that, we are using a backtracking method in which, let's say, we have the feasible MCS pair as shown in this figure, the green ones. And let's say this is the modulation encoding scheme pair that we got through PNESM method. And then we check its feasibility using numerical approach. If it's feasible, yeah, good enough and go ahead. That is our answer. But when it is not feasible, then we go to the next highest weighted sum rate MCS pair and check its feasibility using numerical approach. We continue this process till we get a feasible MCS pair. And this process is called PNESM with backtracking or PB to find the optimal modulation encoding scheme pair. So to find the performance, we are plotting to find the performance of wideband NOMA, we are plotting average weighted sum rate as a function of number of physical resource blocks n. We are plotting this for wideband NOMA and wideband OMA. Here we can see that wideband NOMA performs better than wideband OMA. And we also see that here n equal to 1, flat fading or per PRB adaptation, which has been widely used in the literature, overestimates the average weighted sum rate. So this is the first work. Let's move into our second work. It's multi-user NOMA and sum rate fairness trade-off. So here first look into what has changed and what is next. So in the previous problem, we have considered successive interference cancellation is perfect, but what if SIC has imperfections? We have considered farthest to nearest decoding, fixed decoding order in the previous one, but we are moving away from this fixed decoding order. And in the previous problem, we have considered weighted sum rate as the fairness measure as the objective function, but can we incorporate a general fairness measure? Or to systematically control the fairness, we are proposing or we are using alpha fair utility function, which has been widely used in wireless networks literature. Here we define U alpha of X as follows. Here alpha is the fairness level parameter, X is the rate. So it's for alpha greater than or equal to 0 and alpha not equal to 1, we define it as X power 1 minus alpha divided by 1 minus alpha. And alpha equal to 1, it's ln of X. Here, alpha equal to 0 corresponds to sum rate maximization, alpha equal to 1, which is proportional fairness, and alpha equal to infinity gives maximum fairness. Here, we are plotting utility function as a function of the rate. So here we can see that alpha equal to 0 is a linear function. As the rate increases, the utility function also increases linearly. But whereas for higher values of alpha, we can see that the utility function is not increasing that much. By varying the value of alpha, we can have different fairness levels among the users. Considering these factors, we are formulating the problem statement for a general K-user system, downlink NOMA again. We are using modulation and the discrete rate adaptation and the MCS table that has been given by the standard. And we are allowing any decoding order at each user. So for example, for a 3-user system, the possible decoding orders are as follows. In this 3 to 1 is the farthest to nearest decoding we had discussed in our earlier problem or the commonly used in NOMA literature. And we can also have these other decoding as well. And here our goal is to choose optimal modulation encoding schemes and powers for K users and optimal decoding order subject to block error rate constraint and minimum rate constraints for each of these users. Before moving into the problem formulation, let's first look how to incorporate imperfection at successive interference cancellation in this. In modern wireless systems, we use cyclic redundancy check, and it stops decoding if an error happens. Because of this, we are incorporating block error rate or a maximum block error rate constraint at each decoding stage for a user. So let's say, for example, at user 1, the decoding order is 3 to 1. It first decode user 3's data and then decode 2's and then decode 1's. So here we assign a maximum block error rate each decoding stage can suffer, or it can allow. So epsilon 31, epsilon 21, and epsilon 11. We say that the cumulative, the total block error rate across this process should be less than or equal to the threshold that we have given for the user one's data. So here we can see that, let's say this block is in error, that is corresponds to this first term. And let's say the error happens here. So this is the second term. And let's say the error happens in this stage, that is the third term. And the cumulative should be less than or equal to epsilon. And we get that after solving this, we will get for each decoding or each decoding stage, we can have a maximum block error rate epsilon by 3. When the number of decoding stages are increasing, the block error rate constraint will become more tighter. Here 3 becomes, there are 3 stages. So this is how we are incorporating imperfection at SIC. So let's look into the problem formulation. So to incorporate the general fairness measure, we are using a weighted alpha utility. So we give weights to each user's alpha utility function. So here WK is the weight for kth user, and U alpha of RMK is the alpha utility function for the kth user. And we try to maximize this weighted alpha utility subject to all the block error rate constraint for each decoding stage, and there exists a total power constraint and then a minimum rate constraint. Here, this is for a 3-user system. So the variables, optimization variables are M1, M2, M3, which is again from the discrete finite set, and P1, P2, P3, which are continuous power variables. So again, this becomes combinatorial in nature, and for a given modulation and coding scheme choice, we check whether there exists a feasible power location that satisfy all these constraints, and we collect, or we say that among the feasible MCS pair, we will pick the highest weighted alpha utility as the optimal one. And we also need to find the optimal decoding order, right? So for that, we do the same for all the decoding orders, then we will pick the highest as the optimal one. So let's say there are K users and L modulation and coding scheme choices available. So we need to check the feasibility for L power K possibilities. So for example, let's consider K equal to 2, and there are 3 modulation and coding scheme pairs, scheme choices are there. So in this figure, we are listing all the MCS pairs, and the numbers here is written as for the weighted alpha utility. And here we start, the feasibility check will start with the lowest MCS, and we'll check whether it's feasible or not. And we continue the process. When we find an infeasible MCS pair, let's say 3-1 is infeasible, then we can say that all the higher order MCS pairs are infeasible. Why? Because they require more power. Similarly, we look all the MCS pairs, and we can see that these among the green ones, we will pick the highest weighted alpha utility as the optimal one. And this pruning technique, where we are just discarding a number of MCS pairs without any feasibility check, that pruning method saves a lot of feasibility checks in practice. So among all this process, we'll do for all the decoding orders, and we will find which decoding order has the highest weighted alpha utility. So to find the performance of adaptive order with respect to farthest to nearest decoding order, we are plotting average weighted alpha utility as a function of peak SNR of near user. We are plotting this for adaptive order and F2N order for different K. Here we can see that for K equal to 2, we can see there is a closely match between these two decoding orders. For K equal to 3, we can see a small difference between these two decoding orders. But whereas for the K equal to 4 case, we can see a significantly gap between these two decoding orders, especially at the higher SNRs. And we can see that adaptation helps for higher number of users. So till now we have discussed everything for a given alpha and weights, right? But who is going to give these parameters? For that, let's consider from a system operator's point of view. The system operator always tries to maximize his or her revenue, right? And he tries to maximize the sum rate or the throughput of the system for that. But at the same time, he wants to make sure a fairness level, a decent fairness level among his customers, his or her customers. So similarly, we are proposing or we are formulating a problem for sum rate versus fairness trade-off for NOMA with two users as follows. We try to maximize average sum rate subject to a target fairness constraint. And we tried, using this optimization problem, we try to find the utility parameters such as alpha and weights. Here, we use James Fairness Index as the fairness measure. James Fairness Index for the two users rate is defined as follows, and this index can take a values between half and 1 for two users system. When the James Fairness Index is taking a larger value, we can understand the system is giving more fair allocation. So when x is equal to y, this James Fairness Index have a value of 1, which is maximum fairness. When x is equal to 0 and y equal to 1 or vice versa, it achieves the James Fairness Index as half, which is less fairness. Here, when we plot this average sum rate as a function of these parameters, utility parameters alpha and W2, we can see that the function is non-smooth because of the discrete rate adaptation. And thus we cannot use any gradient-based technique to solve this problem. So we use pattern search algorithm to solve this and find the optimal alpha and W2. To understand the sum rate versus fairness trade-off, we are plotting here optimum average sum rate as a function of target James Fairness Index. Here we can see that as target fairness increases, the optimum average sum rate decreases because we are giving more preference to the far user, and thus the sum rate reduces. And here the red curve is the optimized alpha and W2 for NOMA. And here we can see that it achieves a higher average sum rate than fixing the utility parameters. And we can also see that this blue curve is shown for optimized alpha and W2 for OMA. For any average sum rate, we can see NOMA is getting more, or NOMA is more fair than OMA. So far, we have discussed downlink NOMA system in which base station jointly allocates resources among these users, right? But at the same time, uplink is also equally important, especially in these current generations. Because most of the emerging applications like massive these IoT devices, machine type communication, sensor networks, massive connectivity scenarios, all are characterized by when a number of users are trying to transmit the data towards the base station. These scenarios create a different set of challenges. So we shift our focus, our thesis focus towards uplink and study semi-grand free NOMA. Before moving into semi-grand free NOMA, let's first understand what is grant-based and what is grant-free access. In grant-based access, when a user has to send a data towards the base station, it first gives a scheduling request towards the base station, and then the base station has to give a grant towards the user. Then only the user can send the data. This has reliability and control, but at the same time, it has access delays and signaling overhead. On the other hand, there is no such control for grant-free access. Whenever a user has data, it just sends to the base station. It has low protocol overhead and low latency, but again, it has packet collisions. And in semi-grand free NOMA, we combine the best of both of these schemes. So in semi-grand free NOMA, it allows both grant-based and grant-free users to share the same resources using power domain NOMA. So here, as we see in this figure, this is uplink communication. So there is a grant-based user which has been already scheduled by the base station. And let's say there are 4 grant-free users, and we have to admit one among them to transmit along with the grant-based user. So semi-grand-free NOMA balances grand-based access reliability and control, and it has also flexibility from grand-free access with low protocol overhead and low latency. How the decoding is happening for semi-grand-free NOMA? For that, we have already told this is an uplink and the base station is the receiver and it uses successive interference cancellation. Since there are two users, one grand-based and one grand-free user, there can have two decoding orders. Let's say the grand-free user is decoding first and then it cancelling out from the total signal and then decode grand-based user signal without any other interference. That we call it as F2B order. And the reverse decoding, the other decoding order, we call it as B2F order. For a given scenario, how to choose, how to decide which one to use. For that, we consider both these decoding orders, then we will pick which one is giving the highest rate. That we and this process we call it as adaptive decoding. Here, the next natural question arises that which user we are going to admit for the semi-grand-free NOMA transmission. For that, let's consider there are k users, k grand-free users available, and we have to admit one among them. And for a fairness-aware admission, we are proposing or we are giving a metric called mu k for each of these grand-free users. And we say that we admit the grand-free user which has highest metric mu k. And we propose mu k, the metric mu k, as the ratio of instantaneous rate of that user at time t to the average rate of that user till t minus 1 whole power alpha. Here alpha is the fairness level parameter and alpha equal to 0 corresponds to max rate based, which has been widely used in semi-grand-free NOMA literature. And alpha equal to 1 is proportional fairness and alpha equal to infinity gives maximum fairness. So to find the metric at each grand-free user, we have to find its instantaneous rate, right? For that, we are considering a system model in which there is a grand-based user which has been scheduled by the base station, and there are k grand-free users, and we have to admit one among them. So here we are considering frequency-selective channel and discrete modulation encoding scheme. And we are accounting for the common modulation encoding scheme and power constraint that we have discussed in our first part that has been specified by the standard. And here, since the base station or since the grand-based user is already scheduled by the base station knows grand-based user's parameters such as its power, its channel, and its modulation encoding scheme that meets its minimum rate requirement. Here, our goal is to choose for each grand-free user what is the optimal modulation encoding scheme and power that maximizes its rate, and such that we can find the grand-free user with the largest metric. And to find the optimal modulation encoding scheme and power for each grand-free user, we have to consider both the decoding orders, as I mentioned in the previous slides. So when we are considering F2B decoding order, it first decodes and cancels grand-free user signal. So on the N subcarrier, we can see the signal power, the SNR expression, the signal power divided by interference from the grand-based user plus noise power. And then it decodes grand-based user signal. So on the N subcarrier, there is just SNR expression. There is no more interference. Similarly, we can write the SINR and SNR expression for the B2F order as well. So again, here we are dealing with frequency selective channels, and we will be having a vector of SNRs or SINRs. And to deal with this, we use EESM method, exponential effective SNR mapping, which maps frequency selective channel into flat fading. So problem formulation looks like this. For the F2B order, we try to decode grand-free users data first. So we write the optimization problem as follows. We try to maximize the rate of grand-free user K subject to the block error rate constraint of grand-free user. And this is the minimum rate constraint of the grand-based user. And this is the maximum power constraint. Here we can see that the effective SNR SINR expression for the grant-free user is as follows. Here again, it's nonlinear in power pk, and we use, an approach called bounding approach. For more detail, you can have a look at our ICC Globcom paper. And how we will solve is that for a given modulation and coding scheme, we will check whether the particular MCS is feasible or not by looking these three constraints. And among the feasible MCS choices, we will pick the highest rate as the optimal one. And whereas for the B2F order, we formulate a similar problem, but the only difference is that the constraints are no more same. So maximizing the rate subject to this is the minimum rate constraint of the grant-based user, and this is the blocker rate constraint of grant-free user, and this is the max power constraint. Here, the effective SINR of grant-based user is shown here. Here, PK lies in the denominator. And similarly, we use an approach called law of large numbers based approach to find the feasibility for a given modulation and coding scheme choice. And among the feasible modulation and coding schemes, we will pick the highest rate as the optimal one. So in short, our proposed distributed transmission protocols look like this. So first, the base station checks whether the grant-based user's minimum rate constraint is satisfied or not. If it's satisfied, then go ahead. Otherwise, just terminate the transmission. If it's yes, then the base station is broadcasting the grant-based users' parameters to all the grant-free users. And after hearing this, each grant-free user finds the metric by doing F2B order and B2F order and find the metric as follows. And after finding the metric, each grant-free user is setting a timer which is inversely proportional to the metric. And the timer of grant-free user with the highest metric expires first. In this figure, grant-free user Kate timer is expiring first, and it sends a beacon towards the base station. And after hearing this, both the grant-free user K and the grant-based user is going to transmit together for the remaining coherence time. So to validate our proposed algorithm, we are plotting average rate of grant-free users as a function of average SNR of grant-based user for the F2B order, B2F order, and adaptive order. In all the figures, we are plotting optimal solution, which we have obtained through brute force numerical search across all the modulation and coding scheme and the powers. Here, for the F2B order, we are plotting our proposed bounding approach. And here we can see that bounding approach achieves the same average rate of optimal solution across all the SNRs and alpha values, where alpha is the fairness level parameter. And we can also see that as alpha increases, the fairness improves, and thus the average rate decreases. Similarly, for the B2F order also, our proposed LLM-based approach is optimal. And here, for the adaptive order also, we can see that our proposed algorithm achieves optimality. To conclude this talk, for the downlink NOMA, we have proposed methods for joint power and discrete rate adaptation for K users. Our method was in compliance with OFDM and common modulation and coding scheme power constraint that has been specified by the standard. And it's robust under imperfect successive interference cancellation, and it adapts decoding order. We have also quantified sum rate fairness trade-off for two-user system. In uplink NOMA, we have developed a fairness-aware grant-free user admission and joint rate power adaptation for semi-grant-free NOMA. We did this for frequency-selective and frequency-flat channels with F2B, B2F, and adaptive decoding orders. We have also analyzed performance metrics like average throughput, outage probability, and change fairness for each of these problems. Now, to discuss a few future research directions. In this thesis, we have considered a single cell, single input, single output wideband NOMA system. We can also consider multi-cell, multiple input, multiple output wideband NOMA systems in which we have to deal with more interference. And except for semi-grand free NOMA, we have considered already scheduled NOMA uses. But how to have a fairness-aware scheduling for these NOMA uses? That can be in another future research directions. And in our work, we have considered some rate fairness trade-off of NOMA for 2 users. What if we go to multiple users? And in the last part, we have considered 1 grant free user admission for the semi-grant free transmission. But what happens when we are considering more than 1 user, 1 grant free user? So that can also be a potential future research direction. And looking into our publications, the first we have published our first work in TWC, and the second one we got a paper in TVT, and the third one we have submitted the revision to TWC, and fourth one is under preparation. We have 2 conferences, one in ICC, one in Globcom, and we have also a patent which is based on wideband NOMA systems, our first work. And I would like to thank all of my friends and family members to support me and help me to reach this far. Thank you. Yeah.